All right, so let's go on now. So, like I was saying, said the course content is the nature of light, production of light and measurement, wave properties of light, wave equations, superposition of waves, interference of light, optical interferometry, Fraunhofer diffraction, Fresnel diffraction, and we also consider production of polarized light. And if time permits, we look at the matrix treatment of polarization. For introduction, physical optics, also known as wave optics or wave theory of light, is a branch of optics that deals with the behavior of light as waves. It focuses on understanding how light propagates, interacts with matter, and produces various optical phenomena based on the principle of wave propagation. Now, when you talk of waves, light ordinarily is a type of wave. Light is a type of transverse wave. But now we are studying light as a wave in depth. We have sound wave, we have water wave, we have light wave, we have light still comes under electromagnetic wave. But now we are looking at light as a wave under physical optics. So key concepts and phenomena in physical optics include the wave nature of light. And that is physical optics treats light as an electromagnetic wave composed of oscillating electric and magnetic field, which explain phenomena such as diffraction, interference, polarization, dispersion, based on wave property. So diffraction occurs when light waves encounter obstacle or aperture that are comparable in size to the wavelength of light, which leads to bending of the light around the edges of the obstacle. So that when that happens, the light spreads beyond the geometrical shadow of the obstacle. It keeps spreading. The light ray comes out from a small aperture, a small hole, and then it spreads around the obstacle and then increase like that. Then we have two types of diffraction that we'll still consider in depth. This one is just a preamble I'm giving to you. We have the Fraunhofer diffraction. It's a form of wave diffraction which occurs when field waves are passed through an aperture or a slit, causing only the size of an observed aperture image to change due to the far field location of observation and increasingly planar nature of outgoing diffracted waves passing through the aperture. So the aperture, we are looking, let's say like the keyhole in your door, as small as it is, it will be more pronounced at night. If you want to try it, you can ask someone to put the torchlight at the other side of the door through the keyhole, point it through the keyhole while you are at the other side. to experience what this kind of diffraction is. You will see that the torchlight will pass through the hole and then spread all over the room. The light ray will pass through the hole and spread all over the room. Then the Fresnel diffraction is a diffraction phenomenon where either of an electron source and an observation point, or both of them located at a finite distance from an object. Thus, the incident wave or exit wave cannot be regarded as a plane wave. The first one, Fraunhofer, it can be regarded as a plane wave. For Fresnel, it cannot be regarded as a plane wave. Then for interference, interference arises when two or more coherent light waves superimpose to produce a resultant wave pattern. This leads to formation of alternating bright and dark fringes in the regions where the wave reinforce or cancel each other respectively. So under interference, we'll consider constructive and destructive interference. Constructive interference is a point where two opposite waves superimpose and then amplify themselves to become a bigger wave than it were individually. So at that point where constructive wave is formed, we have bright fringe. But when it is a destructive interference, the two waves, the amplitude of the two waves cancel themselves out, and then that produces a dark fringe. Then for polarization, polarization refers to the orientation of electric field vector of light waves. So physical optics explain how light can be polarized by selective absorption, reflection, or scattering process, and how polarizers can filter or manipulate polarized light. And under dispersion, we'll look at the dispersion, how it occurs when light of different speed varies with wavelength as it passes through a medium. So you might have come across dispersion if you have done prism. When you pass prism through white light, pass white light through prism. When you pass white light through prism, it will give you several colors, 7 colors specifically, what we call Roig beam: red, orange, yellow, green, blue, indigo, and violet. So white light passing through prism will be dispersed to produce 7 colors. So we'll look at that as well. Then we'll look at the waveguide. So the nature of light. Now, light has 2 natures. One is particle nature and 2 is wave nature. That is why whenever light is under study, we say that the wave duality of light. So wave duality of light, according to quantum mechanics, states that all the particles and quantum entities have not only a wave behavior, but also a particle behavior. That is according to quantum mechanics. So the key difference between wave and particle nature of light is that the wave nature of light states that light can behave as an electromagnetic wave. Light can behave as an electromagnetic wave, whereas particle nature of light states that light consists of particles called photons. Particle called photons. So uh, when you see a ray of light or a beam of light, in that beam of light, if you use a sophisticated equipment, you will see the wave nature of light, how light is transmitted from one point to the other in wave nature. At the same time, you will see light as particle behaving as a release of photon. Now, what is wave nature of light? Physical optics treats light as an electromagnetic wave composed of oscillating electric and magnetic fields. It explains phenomena such as diffraction, interference, polarization, and dispersion based on wave properties. So a wave is a periodic oscillation by which energy is transmitted through space. Therefore, wave nature of light states that light is a type of electromagnetic wave. Wave is a periodic oscillation by which energy is transmitted through space. So the wave nature of light is that light is a type of electromagnetic wave. So light, as same as other electromagnetic waves, can travel through a vacuum. Also, it is periodic, which means it is repeated regularly in both space and time, similar to other waves. Light also has a wavelength, that is distance between two waves. And then it has frequency, which is the number of waves that occur per unit second. It also have speed, which we consider as the speed of light, which has a constant 3 times 10 raised to 8 meters per second. So there you see that figure showing us electromagnetic wave. Waves, how waves are formed by both electric field and magnetic field. So the blue light, when light rays or electromagnetic radiation from the sun gets to the earth, as it's transmitted from the sun towards us, this is the way it is being, that this is the path or the way it travels. You see it traveling, but you can't see it with your bare eye this way, except by the use of sophisticated device or equipment or apparatus that you can see it in this way. So we are told that in elementary physics, the propagation of light, that light travels in a straight path. However, if actually light travels in a straight path, would so we are taught light travel in a straight path. So we imagine that the light coming from the sun through the space to us comes to us in a straight path. However, as it were coming to us in a straight path, it exhibits transverse wave nature. It exhibits transverse wave nature. So both electric field and magnetic field both electric field and magnetic field affects the way the light travels. So that is what we are seeing in this diagram. So you see the red color, which is the magnetic field, the blue color, which is the electric field, and then the propagation direction, which is showing us that it is moving on a straight path. It is moving on a straight path. Then from the trough to trough or crest to crest gives us the wavelength. A production of light and measurement. There are countless sources of light, but they can all be categorized under either of the two following categories. We have natural sources and artificial sources. Natural sources and artificial sources. The natural source, as you all know, example is sunlight, while example of artificial source of light is the candle. So now we look at them one after the other. Natural source of light. The universe is filled with objects that emit light. Some light from this source reaches the earth. The following things in nature have the ability to emit light. The sun is the major source of light for the earth. The sun is a massive ball of fire at the center of which nuclear fusion produces massive energy. Now, this energy comes out as light and heat. The light from the sun is one of the major factors behind sustainability of life on Earth. We also have the stars, which produce its own light. However, we seldom get light from the star. In the night, when you look up, you see the star shining. But because it's located very far away from the earth, its impact on the earth is not much felt because it's very far. Then we also have moon. Moon, however, does not produce light, its own light. It's the light it reflects from the sun that gets to us. But we can't rule out the fact that moon also have light. At night, when there is moon, the environment seems to be bright. It's as a result of the appearance of the moon in the sky. So we can still categorize it as a natural source of light. Then we have some organisms that produces light, that has ability to produce light. Such organisms are called bioluminescence. Bioluminescence. Examples of them are the fireflies. Those of us that have been to village at night, you see those fireflies flying, making a sound, and then they'll be flying, and you see light, like twinkling star, moving as they move away into the bush. So that is one. We have jellyfish, we have glowworm, and certain deep sea plants. They are all examples of natural source of light. Then lightning is another natural source of light. And then when there's volcano, you see the light of volcano more at night. When there's volcano at night, you will see that the whole environment will be illuminated by the light coming from the volcano. Now, artificial light sources. For artificial light sources, we have three categories of them. These are sources that produce light artificially, not naturally, by some other means. So one of them, the first of it is incandescent source. When certain objects are heated to a high temperature, they begin to emit light. For instance, our house electric bulb, fluorescent tube, when we pass electric current to the tungsten wire in the globe, in the fluorescent tube, it gives light. So that kind of light is not natural light, it's artificial light. Candle is another example of artificial light. We have another category of artificial light, which is luminescent source. Then another category, which is gas discharge source. Example of gas discharge source is neon lamp and sodium lamp. So here we have examples of pictures or images of natural source of light and artificial source of light. The sun, the star, the fireflies are natural source of light, while the candle, the lamp, and bulb are artificial source of light. Production of light and measurement of light. The word light is commonly used or referred to as radiant energy, which produces a visual effect. So light is an electromagnetic radiation propagated with a speed whose value was numerically determined by relationship between electric and magnetic field. So the formula is given to us here. The symbol of the speed of light is c. And c is equal to square root of permittivity of free space and permeability of free space. So permittivity of free space has a constant value of 8.5 times 10 raised to minus 12 farad per meter, while permeability of free space, that is for the magnetic field, is 4 pi times 10 raised to minus 7 Henry per meter. So permeability, which is mu, is for the magnetic field, while permittivity, which is epsilon E naught, is for electric field. So if you substitute in those values and multiply and find the square root, it will give you 3 times 10 raised to 8 meter per second. Now, the amount of energy in each bundle or quantum is related to the frequency F by the equation E is equal to HF. The bundle I'm referring to each, that is a photon. So for each energy of each photon gives us HF. H is Planck constant and F is frequency. H is Planck constant and F is frequency of the light. Now, wave properties of light. The following are the properties of light. Reflection of light. Reflection is bouncing back when light strikes a surface and it returns. That is like reflection. Refraction is bending. Light bends when it encounters obstacle. So we have dispersion, we have diffraction, we have polarization, and we have interference. So reflection of light. Reflection is the bouncing back of the light rays after it strikes an opaque surface or any medium through which light cannot pass. So when you point your torchlight to a wall, of course, we know that light cannot penetrate through a wall. So you see the rays of light will strike the wall and return back to you. That is what reflection is. Reflection is the phenomenon in which light travels in one medium, incident on the surface of another returns to the first medium, obeying the law of reflection. So if you look at that diagram, the red arrow is the incident light. That is the light you are pointing to that blue surface. So when it strikes the blue surface, because it cannot penetrate, it cannot be transmitted through the surface to the other side, it will strike and give us the green arrow. So the red arrow produces the green arrow on striking the blue surface. Now, according to the laws of reflection, the incident ray, which is the red ray, the reflected ray, which is the green arrow, and the normal, which is the dotted line at the center, on the surface at the point of incident, all lie in the same plane. So if you look at these three lines, they are together at P. They are all at the same point, which is point P on that surface. On that surface, the red line, the dotted line, and the green line, they are at the same point on that surface. That is what the first law is telling us. The reflected ray, the incident ray, the reflected ray, and the normal at the same point of incident, all lies on the surface. Now, the second law of reflection states that the angle of incidence is equal to the angle of reflection. So you see the angle mark there, I and R. I is equal to R. The angle I is equal to R. Angle I is equal to angle R, according to law of reflection or Snell's law. Now, reflection of light, types of reflection. We have three types of reflection. The first one is regular. The second one is diffuse. And the third one is multiple reflection. So what is regular? When a beam of parallel light rays is incident on a smooth and plane surface, the reflected rays will also be parallel. That is when you have a smooth surface and rays of light strike the surface in a parallel manner, it will reflect back in that same parallel manner. Why? Because the surface is smooth. And that is why it is called regular. Regular. Now, in this case, the angle of reflection of the light is equal to the angle of incidence on the opposite side of the normal to the point of incidence. So this type of reflection will obey Snell's law, or we obey the first law of reflection. So as reflection from a polished surface is called regular or spectacular reflection, as we can see in that image clearly. So the second type of reflection is the diffuse reflection. Now, in this case, unlike the first case where the surface is smooth, here the surface is not smooth. So since the surface is not smooth, the reflection will not be parallel to, reflected ray will not be parallel to the incident ray. So when a beam of light parallel ray strikes or is incident on a rough surface, the reflected rays scatter in different directions. This type of reflection is called irregular or diffuse reflection. In this case, the angle of reflection of light is not equal to the angle of incidence. So this kind of reflection does not obey the first law of reflection, where the angle of incidence is equal to the angle of reflection. So reflection from a rough surface is called diffuse reflection. And in this case, the image form will be very blurry. But here, the image form under regular case, the image form will be very clear. But the image form in this case will be very blurry. You will not see the image properly. Now, the third case is multiple reflection. A single image is formed when an object is placed in front of a mirror. What happens if we use two mirrors? Like you see the bold lines in the bold lines forming perpendicular to one another. So we have the one mirror lying horizontally, while the other mirror lying vertically, and they are joined together. So when we have a situation such as that, no, we cannot have a single image form. We cannot have just a single reflection. There will be back and forth reflection. One surface will reflect and strike, send the image to the other surface. The other surface will return it to the other surface, and it will keep going back and forth and produce multiple reflections. So since reflective surfaces such as mirror are very good at preserving the intensity of light in a reflection, a single light source can be reflected multiple times. These multiple reflections are possible until the intensity of light becomes low to the point that we cannot see. So the number of images we see depends on the angle between the two mirrors, and is given at that formula. We see number of images is equal to 360 degrees over the angle between the two mirrors minus 1. So for instance, if the angle, as we see here in this image, this is 90 degrees. So if this is 90 degrees, the number of images I should see will be 360 divided by 90, which is 4. 4 minus 1, 3. So we are going to see 3 images. If the two mirrors are at an angle of 60. Then 360 divided by 60 is 6. 6 minus 1 is 5. So we are going to see 5 images and so on. So refraction of light. Refraction is a bending of light as it passes from one medium, transparent substance, into another medium. Refraction is a phenomenon in which there is a change in the speed of light as it travels from one medium to another. And there is a bending of the ray of light. The refracted ray obeys the following law. Now, what this is telling us is that if I have a stone in my hand and I throw the stone forward, the rate or the speed at which that stone will move in air will be different from if I throw that same stone inside river. If I throw that stone inside river, immediately the stone, it may be going with high speed or top speed. Immediately the stone enters the water, the speed of that stone will slow down and the direction of that stone will change. The direction will bend away and the speed will slow down. Now, this is so because the two mediums are not the same. The air and the water are two different media. So if I'm moving from, the air is of a less dense media compared to water. Water is more dense. So if I'm moving from less dense to more dense, in both cases, the speed will change, the direction will change. But now we need to know the direction, whether it will bend towards the normal or bend away from the normal. If you look at the diagram there, you'll see that the red arrow, which is a ray coming from air entering inside a pond, you'll see that the angle at which the incident angle is larger than the refracted angle. The ray bends towards the normal because you are moving from a light dense to a more dense medium. If you also look at the pencil inside that beaker, you see as if the pencil has been cut into two. But it's not. That is what refraction can do. So according to the law, the incident ray, which is the red arrow, the refracted on the surface, the refracted ray, which is the red arrow inside the water, and the normal, which is a black dotted line to the surface at the point of incidence. That is at the top, at the surface, all lie in the same plane, all lie in the same plane. Then the second law states that for the given pair of media and for the light of the given wavelength, the ratio of the sine of the incident angle to the sine of the refracted angle is a constant. So sine I over sine R is equal to a constant. Sine I over sine R is a constant. So from This expression that we have there, N is refractive index, C is the speed of light in a vacuum, and then V is the speed of light in a medium. Speed of light in a medium. So according to the Snell's law, if you look at that diagram, comparing to the previous slide, sine theta 2 over sine theta 1 is equal to N1 over N2. N1 is the refractive index of the less dense medium, that is air, while N2 is the refractive index of the more dense medium, that is water. Or we can say that N1 is incident refractive index, while N2 is refracted refractive index. So interference of light. Interference is a natural phenomenon that happens at every place and at every moment. Interference is a phenomenon in which two waves superimpose to form the resultant wave of the lower or higher or same amplitude. Sorry. The most commonly seen interference is the optical interference or light interference. The most common example of interference of light is the soap bubble, which reflects white color when illuminated by a light source. And then we have example incandescent bulb generate a wide range of frequency of light, including all colors of rainbow. Condition for interference of light waves. For sustained interference of light to occur, the following condition must be met. One, coherent sources of light are needed. Two, amplitude and intensity must be nearly equal to produce sufficient contrast between maxima and minima. We'll talk about more of maxima and minima later. The source must be small enough that it can be considered as a point source of light. Number four, the interfering source must be near enough to produce white fringes. Five, the source and screen must be far enough to produce wide fringes. Six, the sources must emit light in the same state of polarization. The source must be monochromatic. So monochromatic means just a single source of light, not light that would divide. So example is a laser light. A laser light. If you have seen laser light, like those laser that children used to play with, red, pointing red at night, is all in a football pitch. Sometimes you see a laser green or red pointing to the referee from a far place. You see that it will go straight. It will not split into different colors. If it's red, if it's green, it will go straight to the point where, or to the location where you are directing it to go. So superposition principle must apply as well. Now, we have said the light source must be coherent. So what are coherent sources? The source which emits a light wave with the same frequency, amplitude, wavelength, and phase, or having a constant phase difference, is known as coherent source. So when a light source has a constant frequency, amplitude, wavelength, and phase. It does not change. The wavelength does not change with time. Wavelength does not change with frequency. And with time, the frequency does not change with time. The amplitude does not change with time. The phase difference does not change with time. It remains constant. That is a coherent source. Two sources are said to be coherent when the waves emitted from them have the same frequency and have the same phase difference. Then they are said to be coherent. If you look at the figure there, the diagram shows two wave sources. There, you see the amplitude, the wave, the phase difference, they are all the same. So we say that this is coherent source. So a coherent source forms sustained interference pattern when the waves superimpose and positions of maxima and minima are fixed. That is laser light and sound waves produced from speakers. Sound waves produced from speakers. When sound waves produced from speakers, for speakers, except when you are using microphone and the battery is weak, that is when it may not produce a constant frequency, a constant wave. But if the battery is still very good, you will use it and the sound it produces will be constant, will be the same all through. Characteristics of coherent source. We have two characteristics. The wave generated have a constant phase difference, and the waves are of a single frequency. Single frequency. Example, laser light is an example of a coherent source of light. Sound wave is another example of coherent source of light. Now, incoherent source. An incoherent source emits light wave having different frequency, wavelength, and phase. So, for instance, we have tungsten filament lamps and normal fluorescent tubes. They are incoherent source of light, but laser light are coherent source of light. Okay, let's just take remaining two slides before we call it again. Types of interference. Interference of light waves can either be constructive interference or destructive interference. Constructive interference takes place when the crest, that is the topmost part of the wave, that is crest, then trough is the bottom part of the wave. So that is like maxima and minima, the maximum amplitude and the minimum amplitude. So crest is the maximum, while trough is the minimum. So when the crest of one wave falls on the crest of another wave, such that the amplitude is maximum, this wave will have the same displacement and are in the same phase. So if you look at the figure there, the pink and the green, they look alike, though different colors. So if you join the two of them, wave X and wave Y, it will give you wave Z. The height of wave Z is double each of wave X and wave Y. So it's just like adding 1 + 1 gives you 2. So when that happens, 1 + 1 gives you 2, we are saying that is constructive interference. But when you subtract, 1 + -1 gives you 0. That is destructive. So look at this. In destructive interference, the crest of one wave falls on the trough of another. If you look at wave X and wave Y, the top at the beginning, wave X has a maximum, while at the beginning, wave Y has a minimum. So if you put them to, if you add them together, they will cancel each other. It's just like a positive and a negative will cancel. So that is why the outcome, you see the outcome form is a straight line. That is a destructive wave. So we are going to end our class here today. Now, for your attendance, send your name, matric number to the chat. Your name, matric number to the chat. And also, listen, I have live streamed this lecture in YouTube. While we are having this class, it was also going on in YouTube. So I'm going to send the YouTube link to you so that on your own time, you can go back to the YouTube and listen to the lecture. But when you get to the YouTube, remember to click the subscribe button. Remember to click the subscribe button so that subsequent lectures, when we have it, you will just get the prompt and you always go to the YouTube channel and listen over and over again. Thank you.
Thank you, sir. Have a nice day, sir.
I'm waiting for the rest. Maybe they are not here. They just log in and disappeared.
Thank you, sir. Thank you, sir.
Once I end the class now, it means they are absent. I'm seeing only God's power, David, Ali Olani, Ibrahim, Farah Made Odunayo. 1, 2, 3, 4, 5. You are 7, but it's only 5 names I'm seeing. So the other people did not, they just log in and disappear. So class rep, I'm going to send the link to class rep so that that is the YouTube link so that you be able to go back